Gracias por la presentación. I'm very happy to be part of this community and to show you a little bit out of my world what I'm doing with coffee byproducts. Currently I'm earning my money at the IBP at Hof University, and to Twin Screw, my baby, I bring the money, you know. So that's where I'm working on. Well, materials and especially plastics have a huge influence and play a huge role in our everyday life. You know, sometimes we even do not recognize that. And what you see here is we see perfect biocircular material, wood, right? And we see this, the residues of a fish net made from a persistent polymer. And that's the problem today, that we found polymers, plastics, on places where they actually shouldn't be, right? In the sea, in even higher concentration in the soil, in our blood, in our body, right? Everywhere. And we just have started to understand these negative impacts of plastics on places where they shouldn't be. So that's why I'm working with bioplastics. What you see here is the monomer unit of so-called polybutylene succinate. It's an aliphatic biopolyester, which can be made by bacterial fermentation of almost every cellulose resource. Okay? Its only problem is that it is susceptible to oxidative degradation. Sure, because nature wants to degrade it and bring it back to circularity. It usually is induced by hydrogen abstraction of the methyl group next to the ester group, here, right? And so an oxidation can start. Yeah? Usually it's been triggered by external factors like UV light, for sure the oxidative atmosphere, the humidity, and also heat, because we process materials and therefore we have different processes where we need heat. What you see on the bottom is a potential application. Okay? So what happens now when we have these free radicals? Oxygen is happy and we have oxidation. And we have chain reactions, right, on molecular scale. And on macroscopic scale, what happens is that we get microcracks and they propagate and become macro cracks. So the product fails. And this is what we try to prevent as long we want to use the bioplastic, right? So that's why we are happy to have antioxidants. And what they do, they reduce these free radicals by own but less stable radicals, right? Or they scavenge the once oxidized places and they eliminate these points, with the result that our polymer product is longer stable and resistant to degradation. But if it nevertheless gets uncontrolled to the environment, it has the chance to fully degrade in at least a shorter period of time with less negative impacts. By the way, don't drink your coffee out of plastic cups, but I guess all of you know that already, right? Okay, the sad reality is less than 1% of all plastics, and there are billions of tons produced every year, are bio-based. Right? And with the additive, it's the same sad situation. With regarding the antioxidants, I think there's no bio-based alternative at the market today. So this is a quite sad reality, and you don't want to know how many shit is sometimes in our plastic products today. And I have the same problem as Katrin said. A lot of toxic additives are allowed today, but natural additives are not allowed because they are not on the positive list. So it's a really crazy situation, right? Okay, because nature has so much beautiful antioxidants. I don't want to talk about everyone because I'm not a chemist or an expert in this, but I try to learn and understand, right? But I see it like with our body. We are all meant to drink juice, drink coffee, antioxidants to reduce free radicals in our body, right? And the same, theory is what we want to do with the polymers. We don't want to use the synthetic ones, right? We want to use the natural one, especially vitamins and the polyphenols. Okay, so let's start with the whole process chain of coffee production, right? So, for sure, at first we have the cultivation, right? And you are the experts. I just found that out from theory. I tried to learn and absorb all this knowledge because it's so interesting to understand everything about that, right? You know the influences of climate change now, the influence of region, altitude, climate. There are a lot of nice work from other researchers. We know that the soil quality has a huge impact, not just on the quality of the coffee and the sensoric properties, but also on the antioxidants. And for sure also the variety, the peel color, anthocyans in the outer peel, you can imagine, play a huge role for the type and concentration of antioxidants. For sure, the byproduct itself, we have learned a lot about byproducts. I just will show you the most important ones that I'm working with the associated dry rate, you see that. And there are a lot of nice antioxidants inside. They vary in the type, they vary in the concentration, but most of them are found basically in all of the byproducts. Yeah? It's like the tannins, it's for sure also the caffeine, right? But it's also catechin, epicatechin, for the flavonoids, and for the non-flavonoids, especially the gallic acid, curcumaric acid, and the ferulic acid. And for sure also the ascorbic acid, right? Okay, so now we have the pulping, and this is the first point where we generate the first types of byproducts. Yeah, you know, the coffee husk for the cascara, for example, so I called it here COC for coffee cherry cascara. And I basically investigated 4 natural processed coffee cherries. The next one is from the variety Paulina Natural. And I recognized, okay, it's quite heterogeneous. So I tried to separate at first these byproducts and found out, okay, it's consists of coffee cherry for sure, but also of parchment. But I also found out that almost 1/3 of the whole dry weight is green coffee beans or coffee defects. Okay, quite interesting. And I was asking myself, okay, what will be the influence on the final properties in our bioplastic? And there was also coffee wood. Okay, I did it also with the COC from the variety SLN274 or Paradenia, which consists of coffee cherry and parchments, and also from the variety Palado Café Natural, yeah, which is also consists of the same parts of the Paulina, but in different concentrations. Here we have a higher amount of parchments and also a higher amount of coffee wood. Okay, so this we try to keep in the back for the later properties. So then we got the fermentations. This is out of my comfort zone. Therefore, we have the experts here, like Ms. Kiefer, for example, right, who tell something about that. Probably also have a huge impact on the antioxidants. Then we have, in between all these processes, we have drying processes. So we heard that, right, drying, ripening at the farms, brushing, washing processes. And this is already the points where we have to take care for our byproducts and for the antioxidants. Because what we meanwhile know from the theory and of the work of other researchers is that independence of drying temperature and drying time, we can thermally degrade the antioxidants. So we maybe already lose them in the coffee processing product. And this is something we need to understand and we need to consider to get the best out of our byproducts. Then we have the dehulling. You know that we generate the parchments. I was happy to work with a very homogeneous 100% parchment from the fully washed SLN274. And I also work with a pulp natural variety from the Palado Despolpado, which consists of, again, parchment and also of coffee cherry again. Okay? So that was the point where I start. I get the byproducts, and then I ask myself, okay, what do I have to do? I have to micronize at first my coffee byproducts, right? And I use a special system which is called mill drying. So that means all of these byproducts have a residue moisture, right? But hopefully dry enough that we prevent mold growth because it's this high priority. So my target was to bring it to a particle size that I can work with for a good releasing of the antioxidants and for a good homogeneous dispersion in the polymer. Okay, so it's this industrial dry grinding process. So that means we have a turbo rotor system which is working in here. And the special thing is that we preheat the air in a way that we do not really kill all our antioxidants, but we take away the water, and the duration of the material is less than 1 millisecond in this turbo rotor. So this means it is very sensitive to our coffee byproducts, right? We have this cyclone where we take away the very, very small particles, and then we can take away our fine grinded material. And the way it looks like is like that. So we got now these fine powders from all these coffee cherries, from the parchment, and also the silver skin that I investigated. If something is a little bit different now from our original presentation, but okay. And what I did at first is I investigated the physical properties. So how is the solid state of my powders? I investigated the particle size. And you see, coffee cherry, quite homogeneous distributions, okay? And with the parchment, we see already there are some difference. And I found out there are 2 critical particle sizes. Very, very small particles, less than 1 micron, have a negative impact because they have a big surface, you can imagine. And it means whenever we transport or process them, yeah, they are under friction. And so they electrically charge. And this leads to adhesion, so the particles adhere to each other, right, and produce aggregates, agglomerates. And this can have a negative impact for the mechanical properties. The same with the very, very big particles, higher than 100 microns, like here. They also have a quite negative impact. What you see here, you see the results of mechanical properties. It means we produce these specimens here in a tensile test machine, and then you see here the development of the elongation at break. So that means how much can I extend the material until it breaks. Okay, and what we see here is that we have these two parchments, and you see the orange one have a lower particle size, and the red one from the SLN has a bigger particle size. Right? And we see that from the beginning of 10 weight %, we completely lose our mechanical properties. And this is due to the bigger particles. They have a bad matrix particle adhesion, they build cavities, microcracks, and this leads to a failure of the polymer product. And this we need to consider because we don't want to improve one property but reduce other properties on the other side. Yeah? We need to guarantee that our product is working. Okay, for sure, when we have small particles and high surface, for sure, we also have the risk of the absorption of too much moisture from the humidity. Yeah? And so this can, again, increase the risk of mold growth because we need to store our byproducts when they are fine powder, right, for a couple of days or months. And on the other side, we need to guarantee they are very, very, very dry. I'm sorry. They are very, very dry. So that means we don't want to have any residual moisture. Why? Because when I bring them to my extruder, in the polymer melt, we have temperatures of above 100 degrees Celsius. So that means evaporation of moisture, right? And this can lead to air bubbles, cavities. And they are, again, failure or optical problems, and this we need to prevent. So what else do? We do chemical characterization. You see here the results of the total polyphenol content. And basically, we can say coffee cherries have the highest amount of polyphenols. And the parchment here in that characterization the lowest amount. We will see later that the difference. Basically, the difference in between the type of byproduct can be explained by the different concentration. You remember COC, PDC had a high amount of green coffee beans compared to the coffee cherries, for example. And PMT, PDD consists of some parts of coffee cherry and so has a higher concentration of total polyphenol content. On the other side, we do a lot of thermal analysis. Right, and what I just want to say is when we extrude our polymers, we are in the temperature range of roasting, actually. So more or less what we do with our coffee byproducts is some kind of roasting. These byproducts spend in between 3 to 4 minutes in the extruder, right, and heat it up, and so you can guess something will happen. And what we see is also, and investigate, is the brown discoloration, right, and you see, especially here with the COC Palhina, we remember it has a high concentration of green coffee beans and coffee defects, so it starts with the earliest with the brown discoloration, right? So, and this is probably due to Maillard reaction. This is something I need to understand more, and here I'm happy if someone can come to me and investigate together these effects because the reduced sugars have, I guess, a huge impact on the final properties. Okay, let's come to the compounding. So this is my main business. What am I doing? I always say it's like cooking. Okay, I have a big machine. It's called compounder with a co-rotating twin screw inside. You can have special configuration. You transport the polymer. You try to have a sensitive molten of the material, and then we add the coffee byproduct, right? And it's like cooking, so that I have my different herbals and bring them because of UV protection, right, and all these kind of stabilization. So I bring them via a side feeder into my polymer melt. The polymer melt starts to get viscous, and then I try to distribute homogeneously this mix of material, and finally I got this biocomposite, and I can now granulate that and can go to the next process, like processing, for example, I produce a filament for 3D printing of these coffee cup made with coffee byproducts, okay? Something to play with. Okay, and now we can take the granule to investigate, did I really optimize my stabilization, so my antioxidative properties. And what you see here is the result of the DSC, differential scanning calorimetry. So that means we heat up our biocomposite in an atmosphere of oxygen, right? And when we have no stabilizer, this time here I have another very potential bacterial fermented biopolymer. It's a polyhydroxybutyrate co-hydroxyvalerate, so basically polyhydroxyalkanoates and different copolymers of that, okay? And it's a very good candidate to replace all stiff polymers, right? The PBS that I presented is a very good candidate for replacing polyethylene, polypropylene when you heard about that. And what we see is we see this exothermal reaction at a certain temperature, right? When we have no additives inside, like this here, this exothermal reaction. And this can be traced back to oxidation, right? And what we see is when we add, for example, 5 weight % of the parchment SLN, this has completely been taken away. So that means we have no oxidative degradation. What we unfortunately cannot prevent right now is this endothermic peak, and this is due to thermal degradation, pure thermal degradation. Yeah? This is also something we try to work on so that we can also use our bioplastics for higher temperature application. Right. Yeah, and the same we also did with the polybutylene succinate. Here it's just important to focus the material when it is unadditive, so the PBS neat, like this here. And we have also measured in the DSC. It's called dynamic oxidation induction temperature. So the temperature when the oxidative degradation starts, and there are 2 different methods called onset and offset. And what we basically can say, and this is what we are happy about, is that all of our coffee byproducts optimize the stabilization against oxidative degradation. This is very, very nice for future aspects. But there are some candidates with a very, very good performance, like, for example, the COC from the SLN, from Bata Estate, and also the associated PMT from the fully washed process. And this is quite interesting when you remember that this PMT was the material with the lowest TPC value, right? So, and I asked myself, okay, what was happening? And then we started doing also microscopic analyzation. Yeah, we investigated the native materials and also the fine grinded powder. And from literature and also from own investigations, we meanwhile know that the parchment consists almost of dietary fiber, right? 90% are fiber content. And even when we have fine grind them, the fiber are still stable, right? So we also calculate aspect ratio, different geometry and things like that. And we could find a very, very good accordance to the results of other researchers that could show that these fibers contain antioxidants, but they are insoluble. So that's why I couldn't find them in the TPC measurement, right? But what other researchers could show is that they can be released under a certain circumstances, and this means temperature, right? So here in this example, we have the ferulic acid and the coumaric acid, and we could see and show that via the breaking the bonds of these linkages, we could show that in the moment in the extruder when the antioxidants are not released, but the biopolymer starts to degrade, right, due to a higher temperature, due to shear, due to oxygen. Now these antioxidants are released from the fibers, and now they reduce the free radicals in the biopolymer and scavenge the oxidized points, right? And so it's a perfect match of releasing the antioxidants that been projected also in the fibers, and the PBS, for example, in that case, that is need to be stabilized. So a very, very good match. So just to summarize, we have a huge influence of the coffee processing on the homogeneity of the coffee byproduct. So this is something we can talk with the farmers, with all the people in the coffee production chain. For sure, also the influence on the presence and content of polysaccharides and reduced sugars. So this is probably something we really need to think about, because I have a lot of problems sometimes to extrude materials, like with the cascara. It's probably very potential, but this Maillard reaction is a polycondensation, so we produce water, and this probably leads also to creation of cavities. So it's sometimes very hard to extrude that. Also, time presence and concentration of antioxidants is relevant, right? And this antioxidant efficiency highly depends, as we have seen, on the type of byproduct, on the presence and solubility of the antioxidants, of the milling process, particle size, and for sure also on the thermal treatment during drying and extrusion. Right. That's the point I want to say. Yeah, thanks to everyone who's working in that field and trying to make the world a better place, especially with coffee. And that I'm always looking for new samples, right, for new fully washed parchment, if someone have of COC of different peel colors. Usually I need minimum 2 kilograms, so it's always a logistical problem, right? And nevertheless, I'm looking for applications like these 3D printed cup, for example. So if anyone has an idea or a project, let's talk. Thanks.
Thank you very much, Mirko. very nice presentation. Then what do you think, what is the best one, the best option for you of the byproduct that you have studied?
Yeah, surprisingly, the PMT. At the beginning, I was a little bit laughing. I thought, maybe it has had not the best performance. Do you mean that, or?
Yes, I agree.
And,
Amaya has in her thesis something about that, and I think that the link nanos are making you happier with the antioxidant properties.
Exactly.
Yes.
Yeah, what we see is we have a change from the beginning to the end. We have also a change. Antioxidants become macro radicals, right? They also change, and this is something I need to understand more. But what I've learned so far is that really the antioxidants are protected itself into the fiber and are then released when I need them. So it's really a very nice marriage between polymers.
It's because they are part of the lignins, and then it's very hard just to release them, and then you need a very aggressive treatment. But it's a very nice, I think, material for that because it's very dry. That means that you can take it and you don't need too many, conditions just to storage them before to be converted into the bioplastic. And because we have another option in the coffee for the food, I think that one should be for the parchment, the best one option in my personal opinion. What do you think? Questions for this very nice presentation? Okay, go here.
Thank you very much. It's a short question. Did you use polylactic acid for your biopolymers?
Yeah. I also use polylactic acid. I have some samples with me. If you like, I built up a small sample show with different, and there's also polylactic acid. Polylactic acid is probably also very potential. I don't like it so much yet because we need to process it at higher temperature. That means at 220, 230 degrees Celsius, and this is already a range which most of the byproducts do not like so much. Right, like with the coffee, you also should not process it at too high temperatures. But it's working, but limited.
Second question: are you going to prepare filaments for some 3D printing or something like that?
Yeah, we produce our own filaments. But currently, if I would bet some money, I would go to a direct 3D printing with the granulates, so that we do not have the production of the filaments, which is good for home 3D printing. But it's another processing, another energy, another temperature, another treatment. So it's possible to go directly with the granulates. But yes, we also produce filaments.
Thank you very much.
Okay.
Time? Yes.
So thank you for the presentation and really letting us, or at least me, discover like a new world. So thank you for that. But my question is, I guess it is a big world of research in the bioplastics. How would you place coffee as a good candidate for raw material for bioplastic in comparison with other raw material?
Yeah, that's a good question. Yeah, at the end of the question, it's a question of economics and logistics. No one would start with a material that hardly exists, but we know we have a lot of coffee. We have a lot of coffee byproducts, so a big potential for the people at the farm to work with. So we can use the residues. We should think in cascades, like which of the byproducts can become food again, right? And when it's maybe not good enough for food or has not the allowance at the moment, maybe we can think about material usage, right? Then we can think about using the heterogeneous residues for polymerization, because bacteria are not so like ATP, so they say we take everyone which is cellulose no matter what, right? So when we have heterogeneous streams, we can take this, and there is even another residue which can be taken for energy recovery and things like that. So this is the way we should think about, and we do that not to bring the coffee byproduct from the farm to Germany to use them as stabilizers, but we should bring our knowledge to the farms, to the countries, to prevent soil pollution, seed pollution, and things like that. And that's why I would think there are a lot of potential, and we should keep them. We should not burn them or throw them away. What sometimes is happening at the farms, I think.
I think that because there are many countries that they made the wet process, you have a lot of parchment because it's something that you have in the way to obtain the green beans, and then I think that you have material, and makes sense just to go there, just to make the production. If you use a very simple way for the production, if we adapt our mentality to how they can produce in an easy way, and you do, I think.
But this is exactly the problem, why it's also increasing so small. Because I cannot work with just a few grams, but I also cannot work with hundreds of tons, and this is the field I'm working with. So is there someone who needs the amount that I can produce per day? This is my bottleneck at the moment, the logistic of all these questions.
Good. More questions? Yes?
Yeah, you said at the beginning that there is like you showed this picture of the net in nature. So do you also do studies on how you change the biodegradability of the bioplastics with the antioxidants?
At least we work together with Theo Berlin. We have a good friend who's working with microplastic influence on soil quality. And this is always good. I give always, before he published some of his results, he called me, hey, don't work with that material anymore. Okay, I do that. So this is very interesting. At least we need to guarantee that we do not verschlimmbessern, we say in Germany, you know. So this is really important for us. Do we have a really good degradation? Do we have no toxical influence? And so yes, we try to prove that and guarantee that, to find the balance. This is always, you know, the question exactly. How stable must it be to guarantee the product application? Can it be degraded also in a couple of days?
Okay, thank you very much for your nice presentation. On the interest of the audience, time for the coffee, and we can continue the discussion during the break. Okay, bye.